All right, so back in the day, before calculators, question might be like, how are you supposed to find the sine, the cosine, and tangent? People, scientists, mathematicians used these values all the time, astronomers especially, like being able to plot the positions of stars and stuff like that, because stars, they control us and stuff in an astrological kind of way. Well, on the previous example, we knew all the sides of the triangle. We can just list the three trig ratios for those sides using whatever angle that we had. But, usually we have a specific angle measurement. We have 35 degrees, and we're missing one of our sides. That's how we usually use it. So, of course, we would use a calculator in order to call up what the sine, the cosine, tangent is. But in the long, dark years before the calculator, people had to find their trig ratios in a table. It's a trig table. So here's an example of one. So in the 1500s, 1500s, that's during the Renaissance. George Richticus, a student of Copernicus. Copernicus, very, very important scientist. He's the one who came up with the Copernican system that explained that the Earth was no longer the center of the solar system, that it was, in fact, the sun. Very, very controversial. Anyway, he was the first to define the 6 trig ratios, the trig functions, in terms of right triangles. So prior to this, trig did exist, but it wasn't tied to right triangles. This was the first guy to tie those things together. He also started a book of trig values for these ratios, accurate to 10 decimal places that they could use in astronomical calculations. Let's look at our calculator here. Call it up on your own calculator. Let's say, for example, I take the sine of 13.1 degree. Whoa. Hey, what are you doing? Try that again. The sine of 13.1, yeah, degrees. Let me hit approximate. And you see how many decimal places I got there? That's about as accurate. Let me see. Let me count these up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, this is a little bit more accurate. I can actually set how accurate that was, maybe to something like that. And then I've got as accurate as George Richticus's book it would be. Come on. Let me approximate that again. All right, so that's about what he would have had in his little book, right? Something like that. It's about as accurate as your TI-84 calculator was, too. But he did this back in the 1500s. The question is, like, how did he do it? Like, what was he doing? How did he actually do it? All right, back over here. So he died before he finished his book. You can imagine the enormous undertaking that it would possibly be. It was his student, you can see his name here, Valentin Otto, that finished the book. It ended up being 1,500 pages. Geez, that's a big, thick book. It's not like a Stephen King novel. It's totally boring. All it's got is a whole bunch of angles and trig ratios for each one of those things. So in this particular sample over here on the corner of a trig table, you can see there's only 4 decimals. His would have had 6 more decimal places of accuracy on that. And just as an example, this is how you would use it. Not like this. You wouldn't pull up your calculator to use it. What? So if I wanted to find, first of all, you take out your crayons. There we go. The sine of 13.1 degree in my table. Now I'll pull up my highlighter. Here's 13, but you can see that on the left-hand side, the degrees increase by tenths. So 13.1 is this, that row. And the sine, hey, where are you going? The sine is the first column, which means that the sine of 13.1 degrees is about 0.2267. I said 7, but I wrote a 6. Let's see what the calculator said for us. And of course, we have more decimal places, kind of like pi or the square root of 2. A lot of these are irrational numbers, meaning that the decimal places are just going to go on and on forever. So I'm going to show you one of the ways that you could possibly come up with some of these numbers, and that's just by drawing out a right triangle, right? That's basically what we're going to do here. No, that's not the right thing. I want to go in here. Yeah. Okay. So let's say, for example, I just drew this right triangle. I used a protractor, I used a ruler, as accurate as I could, and I just got it to the nearest No, not even the nearest tenth. I just rounded everything to the nearest centimeter. So I got 5 centimeters for one side, 14 centimeters, and 15 centimeters. So let's use these numbers in order to calculate the sine, the cosine, and tangent of 20 degrees. Okay, so the first thing that I want to do, of course, is reference my 20-degree angle so that I know which one of these is supposed to be my opposite side, which is this one. It's the 5. That leaves the 14 as being the adjacent side. And of course, the 15 is our hypotenuse side. If I wanted to find the sine of 20 degrees, that should be equal to opposite over hypotenuse, which is 5 over 15. That's the same thing as 1/3, which is 0.333. Let's look in the table. So in this particular table, 20 is just right down here at the bottom, and you can see that for the sine in the first column there, it's 0.3420. Let's see what it is on our calculator here. That's got a lot more accuracy. The sine of, inside there, I'll put 20. Let's hit my degree button and approximate this. And you can see I got a lot more decimals here. So it's not terribly accurate, right? Our little approximation was not terribly accurate. Let's do the same thing for cosine. The cosine of 20 degrees. Cosine, its ratio is supposed to be the adjacent, which is 14, over the hypotenuse, which is 15. 14 over 15, not doing that one in my head. Calculator will do it for me. 14 divided by 15, approximately equal to 0.933333333. Of course, 933 ish. All right, and then here it is on the table. Yeah, oh, this one looked like it's a little bit more accurate than we had the other one. Just a teensy bit more accurate, and the calculator, of course, is going to give that to us as 20 degrees approximately. Bam. All right. Last one is our tangent. Tangent of 20 degrees is equal to, let's see, tangent is supposed to be the opposite over adjacent, another hour, which is 5 over 14. Oh, it's pretty close to the sine on this one because it's 5 over 15 versus 5 over 14. Huh? 5 divided by 14. Approximately 3.57. And what was it on the table? 0.357. And then what is it actually on the calculator? What is tangent of 20 degrees-ish? There you go, right? All right, so that doesn't seem very accurate. If I'm just measuring to the nearest centimeter, each one of these numbers doesn't seem very accurate as finding the value of sine, the cosine, and tangent. So how could I improve that? Well, obviously, I can improve it by maybe more accuracy in each one of my measurements. Maybe instead of to the nearest centimeter, I measure to the nearest tenth of a centimeter. And that's not too hard to do, right? I've got rulers that measure to the tenth of the centimeter, which is a millimeter. So now I've got 5.1, 14.0, and 14.9. A little bit more accurate, a little bit more precise for our measurements here. So now I'm not going to do all of them because otherwise this video is going to take forever. I'm just going to do sine. Let's just focus on sine. Sine of 20 degrees now with my opposite in my hypotenuse is 5.1 over 14.9. A little bit more accuracy. Let's see what that is. 5.1, 14.9. 9, I think it was? Yeah. Okay, so, and look at this one. 0.3423 if I put 4 decimal places. So 3423. All right, let's look at it back in the table again. Well, I don't need to go that far. It's just the first one. There we go. And you see I got a lot more accurate there. All right, and so again, I can increase the accuracy just a little bit more on the next one where, bam. Or maybe even this one. Let's get even crazier. Let's get 3 decimal places of accuracy. Let's see what the sine ratio turns out to be with these new numbers. Skip that one. We're not playing here. Let's take, dang, every single time, the sine of 20 degrees with this triangle to approximate the sine. Okay. 5.104 over 14.023. Am I going to remember those numbers? There's very little chance that I'm just going to call it right up here. Have something to look at. And then call up the calculator again. And then let's divide these numbers. I have 5.104 divided by 14.023. Is that right? Oh, no, because I just divided it by the adjacent side instead of the hypotenuse side. What ratio did I just get? I got opposite over, that's the adjacent side. I just got tangent. That's not the one that I wanted. I want 5.104, and I want to divide that one by the hypotenuse length, which was 14.923. There we go. So now take a look at that number, 0.324022, and then let's compare it to the sine value of that angle measurement. I'll approximate this. Let's see. And you can see, ooh, look at that. All the way up to that second tube, 3.4202. Pretty accurate there. All right, let me see. Did I actually write that one down right? No, I didn't. All right, let's fix that just in case somebody's actually watching this. This guy who's teaching us doesn't even know what the sine ratio is supposed to be. Okay. All right. Is it very practical that we could measure with that kind of accuracy, though? I don't know about you. Like, my ruler measures to the 10th of the centimeter, as in, like, I could probably get that level of accuracy, but I could never get this level of accuracy. Now, think back to the 1500s. They didn't even have that kind of accuracy with the nearest centimeter yet, right? So they did not. George and his protege, Valentin, certainly didn't use this particular method. Instead, they would have used some sort of calculus. Even before calculus was invented, there was a lot of stuff about sine and cosine and tangent, the trigonometry, lots of different rules, lots of different formulas that they would have used to approach these numbers much, much faster without having to do these measurements. However, this brings up a very important application here in terms of something that you learn in chemistry, which is called significant figures. Sig figs is what we call it. And significant figures is all about how accurate, how trustworthy is my answer. And that trustworthiness of my answer is completely dependent upon how accurate your numbers were to begin with. So in this very first example, I only have one significant figure. That's at 5. Sure, you've got 2 in these other ones, but you always take the smallest one. In this case, it's 5. You just got 1. It's not 5.0, which would be 2 significant figures. It's only 1, which means when you're all said and done, the only thing you can actually trust is 1 decimal place. If you look at the next example, now you have 2 places. I've got 2 significant figures, which means that whenever I go to look at my answers, I do any kind of calculations on these numbers, I don't round it to the nearest tenth. I can only trust 2 of these figures because only 2 of them are actually significant, which is a very interesting kind of application and shows the, I guess, the power of the concept of significant figures. All right, the very last video that we're gonna do has to do with let's just do some applications with sine, cosine, and tangent. Let's do some actual problems where we're solving for a missing side length.